Screen visible to everyone?
Yes, ma'am.
Okay, so this is our next topic, which is solid catalysts. And again, this chapter, you'll find the material of this chapter in James Smith, Chemical Engineering Kinetics. If you have the second edition, then this is in chapter 8. And if you have the third edition, that is also chapter 8 in the third edition too. So what we had seen in the first two topics is in fact, the first topic that we had talked about, where we talked about the features of catalysis, where we talked about what is a catalyst. A catalyst is a material which essentially alters the rate of a chemical reaction. When we say alters, most of the times it is an enhancement and it is not a reduction in the rate. So it improves the rate of a chemical reaction and itself remains unchanged in the process. It has no effect on the equilibrium of the system, of the process. That means the final products that you will get would be the same, but what is going to change is essentially the rate at which the system happens. So what happens is that we follow a different path by which the products are formed from the reactants. So now when we talk about a catalyst, I had shown you a little bit about how a particular catalyst is chosen for a particular reaction. How do we choose a catalyst? And we had seen in a lot of cases that these transition metals are essentially come out to be very good catalysts. And these transition metals, they could be in the form of a metal, in the metallic form, or they could also be in the form of an oxide, depending on my reaction. And so today what we will try to see that we will talk about these solid catalysts in this entire chapter. The preparation, what are the features of a solid catalyst, what are the preparation methods, and finally, how do we characterize this? So the first thing that we are talking about is the general requirement for a good catalyst. So let us see what it is. So the activity, the first thing that we talk about is essentially activity. So when we talk about the activity of a catalyst, that we say it should be able to promote the rate of a desired reaction. So when we have a reaction, if I look at the energy of this out here, if it goes like this, then this activation energy which is there between here, this place and here, that should go down when you're using a catalytic reaction. That means it should be able to promote, that means improve the desired reaction. It needs to absorb the reactant molecules strongly enough for them to react, but not so strongly that the product molecules stick more or less permanently to the surface. So that means what? Suppose we have a reaction that is where we have the reaction is equal, say for example, A going to B, and this is happening on a catalyst site which is out here, then A comes out here. So you should be able to absorb A on this particular catalyst site. They should absorb sufficiently strongly for the reaction of A and A to B to happen, but not so strongly that the product molecules, that means the B which is formed out here, when it goes out, it should be more or less, it should be able to go out from after, that means it will get dissolved from the adsorption site. So the attraction out here of the product B to the catalyst site should not be so strong that the release of B is hampered. So it should be strong enough for it to react and get absorbed and then react, and then it should be weak enough for it to get dissolved from the surface. So the first thing that is important out here is the activity of a catalyst. So for a good catalyst, we need something which has got a high activity, or the catalyst should be active for a particular desired reaction. That is the first thing. The second thing is called selectivity. So what is selectivity? That suppose we have a reaction like this, which is A going to B, going to C. I have written a series reaction. We can also have a parallel reaction, and B is my desired product. Then the catalyst should be such that it promotes this first step, that means A to B, and it should not promote the next one, that is from B to C. So this should not be encouraged, and they should only encourage this part of the reaction. It should be able to promote only the rate of the desired reaction, and retard the undesired reaction. Suppose we have a parallel reaction happening, for example, A going to B and then also A going to C, where B is my desired one. Then the A going to B, this reaction should be promoted or they should be enhanced, whereas this one should not be enhanced. Selectivity sometimes is considered to be more important than activity and may be more difficult to achieve. You can have a highly active catalyst. What when you say highly active catalyst, that means the reaction of A going to B is here gets completed to A going to, for example, this particular reaction gets completed to say a 95%. So you can say the activity of the catalyst is high. But if the formation, once we analyze the product, we see that this 95%, most of it is formed as C, which is not my desired product, then the selectivity of this catalyst is not good. So if the selectivity is not good, then there is no point, because what we need is actually this desired product B. So activity is important. That means you want high conversions. That is important. But selectivity, whatever is converted, the maximum amount of that, if there are more than one product, maximum amount of that should be your desired product. So the selectivity is the next most important thing when we talk about a catalyst. In fact, even more important than activity sometimes. Then comes the term stability. Stability means, I told you that what happens during a chemical reaction, heterogeneously catalyzed chemical reaction, is that, say, for example, A gets adsorbed on the active site and forms some sort of a complex A dot X or something. And then it reacts to form B, which becomes B dot X. And then this B gets released from the surface and we get back our original X site, which is equal to X. Now what happens is that over a period of time, and this should happen every time the reaction is happening. So if this goes on, so that a catalyst should be able to go on forever and ever means it should have an infinite life. But in reality, that is not what happens. A catalyst does not have an infinitely long life. Over a period of time, it tends to get destroyed. Earlier it gets destroyed, that the worse it is at a catalyst. So when I say a catalyst is stable, what it means that it can resist deactivation. When it gets destroyed, the activity of the catalyst gets destroyed. That is called deactivation. So the deactivation is something that is not desired, and a catalyst which does not deactivate is the one that is preferred in our case. So this deactivation, how does it happen? When you have some impurities settling on that active site, when two active sites join together or agglomerate and they fuse and then they sinter and they become one site, then also active sites get destroyed, or some carbon deposition is there on a particular site. So all of these cases, you see the stability of the catalyst is very small. So before we carry out a reaction, we should check it out whether the catalyst is active, whether the catalyst is selective, and whether the catalyst is stable. A high value for all three of them is what is desired. But sometimes we may not get a high value for all three of them, but then we have to make a choice between what is it. Okay, this catalyst has got high selectivity, but the activity is not so high, but the stability is also good. So we say, okay, it can be used sufficiently well, because even though the activity is not very high, I can recycle and make it into the recycle unreacted product, but at least whatever will be formed is going to be my desired product. So the next thing that we talked about is shape, size, and porosity. Let us see what these things are. What is the shape of a catalyst? See, for example, the most common catalyst that we see is essentially your spherical catalyst. Then we can have something which is cylindrical in nature. Then you can have a catalyst which is like a needle. Thin ones like the needles actually that you use for sewing. So any of these are all right in terms of shape. So catalysts can be of different shape. They can be of different sizes. Usually industrial catalyst will be few millimeters, 10 millimeters or 20 millimeters. That means in terms of centimeters, it will be a 1 centimeter or maybe even less than 1 centimeter in particular size. And the next thing is porosity. That means how porous is it? That means it has got what the gases can go inside these catalysts. Porous catalysts provide high internal surface area, larger number of active sites, and the chances of better dispersion. So when you have a catalyst which is porous, where gases can go inside, it has got a large internal surface area. Porous is essentially, if you remember, I had shown you this picture that if I have a catalyst like this, there will be pores which are inside the pores which are inside this catalyst like this. Let us just do this. So these are a catalyst which has got sufficiently high internal surface area, and it has got a large number of active sites, and there is a chances of better dispersion. So when you have these pores which are there, which has got high surface area, and these pores will have these active sites which are there. These active sites are large in number. The more the pores, the more the active sites, and the better the chances of the catalyst being dispersed. If you remember what is dispersed, what I meant by dispersed is on the surface, each of these active sites should be separate from each other. They should not be close to each other, essentially, like this. So the dispersion, that means if I put, say, 100 platinum atoms, each of these 100 platinum atoms should be available for the reaction. That is what is called better dispersion. Catalyst shape and size should be such that to provide low pressure drop. Now, what are we talking about? Suppose you have a packed bed reactor like this. When we have a packed bed reactor like this, and you're packing it with small catalysts. Now, these catalysts are very small in size. For example, fine like, say, talcum powder. Then they will be packed so tightly that when you pass a gas from the bottom, it will find it very difficult to go from the bottom to the top, and there'll be a very high pressure drop that is there. The pressure drop which you see in this bed is going to be really, really large. So that is not desired, because pressure drop means what? Essentially, then you have to pump the fluids with more energy. So there's a loss of energy when we are talking about pressure drops. Smaller size will give you a large surface area, but it will increase your pressure drop. So we have to choose catalyst shapes and sizes such that the pressure drop is not so high that it is going to cause a large energy loss in our cases. And we will discuss this a little bit more later when you see, if you remember those monolith catalysts I had shown you, these were like, those tubes which are there. When you come to class on Monday, I'll show you a real actual monolith, what it looks like. So they have very low pressure drops, but their surface areas are also large. So we have to start choosing materials based on that. And catalysts should have sufficiently high mechanical strength to avoid breakage during reaction and loading. So the mechanical strength of these catalysts should be high. That means, just imagine when you're packing this bed. Now, this is an industrial bed. This is not something that is like a tube in your lab. Industrial bed, which will have, say, a diameter of 1 meter or 1.5 meters or even 2 meters, and you're dumping like 1,000 kgs of catalyst inside it. So when you're dumping them, obviously nobody's going to put it piece by piece. They're going to pour it from the top. And if these catalysts do not have sufficient mechanical strength, they will break into and break up into powder when we are doing this. Also, when these gases are going up regularly at high velocities, etc., these catalyst particles may come in contact with each other, like there may be attrition, and again there might be breakage. So that is not desirable. So they should have sufficient mechanical strength. So if you look at this picture, if you see that what I have, let me just blow it up a little bit. So this is my catalyst pellet. So the activity of the catalyst is important. It should be sufficiently high, highly active for a particular reaction. The porosity of the catalyst, that should be sufficiently porous, which will have high chemical activity, high specific activity. Specific activity means it should have a high selectivity, which we call. And there should be a surface porous catalyst. Then comes the Then comes the flow distribution. Flow distribution essentially means that your flow should be distributed properly. Again, when I'm talking about these particles, that each of the flow should be distributed evenly through the channels. There should be low pressure drop so that the energy conservation is there, and the mechanical strength should be high. I've just discussed each one of them. And the next thing is the stability. That means the catalyst should be resistant to fouling. Resistant to fouling essentially means that there should not be any destruction in terms of that means the stability of the catalyst should be high. So these three things are very important for a good catalyst: stability, selectivity, and activity. Next, let's look at a porous catalyst pellet. So solid catalysts are normally porous. It is difficult to obtain large outer surface area that is greater than 1 meter square per gram by subdividing non-porous solids into small particles. So suppose this is my spherical catalyst. How you know the diameter or rather the radius of this catalyst, you can find out what is going to be the surface area. So what is going to be the surface area? The surface area is going to be 4 pi r square. This surface area is the outer surface area. No matter how small you make this, the outer surface area that you can get per gram of catalyst cannot be very high. So that is why we have this internal pores that I have repeatedly told you, which helps me to increase my surface area, the internal surface area, which essentially will carry out my reaction. The size of a catalyst pellet used in a commercial reactor typically range from 1 to 10 millimeters. 1 to 10 millimeters. The pellet is usually composed of, that means 1 to 10 millimeters means this is 1 centimeter and this is 0.1 centimeter. So just imagine what is going to be the size of each of your pellets. Just think about it. It is 0.1 centimeters, about 1 millimeter, to about, say, 10 millimeters is what we can have in an industrial level, a commercial reactor. A pellet is usually composed of smaller particles, frequently on the order of 1 micron, that are held together by binders added during the catalyst preparation process. So when we are talking about a catalyst, this is what the 1 to 10 millimeter that we said is this basically this catalyst pellet. Now this catalyst pellet is made out of smaller particles. These particles are of the order of 1 microns. And sometimes you can just make these particles like you would have a tablet by compressing them together. And sometimes that if that does not give it sufficient mechanical strength, then what we do is we add a binder to it. If you remember in the last, when we were talking about catalysis, the last few terms I discussed about had this term called the binder, which is out there. So this binder essentially helps to hold these catalyst particles together to form it during the pellet formation. These smaller particles are usually porous and contain, now these particles which are there, each one of them, we take them up. If I blow up one such particle, then this is what I get. And they have pores inside, just like it is drawn out here. Now, these pores are of different sizes, and because they're of different sizes, they have different names. Particles, or sorry, pores which are less than 2 nanometers in size are known as micropores. Ones which are less than within 2 to 50 nanometers in size, those are known as mesopores. And macropores are those which are greater than 50 nanometers in size. They can also exist, which can be dependent on the size and packing density of these small particles. So macropores, micropores, and mesopores. Most of the times you will see that inside the catalyst particle, there will be micropores and mesopores. And so if you think about it, we'll discuss this again more and more, that there are pores inside this, within the catalyst particle, and between two catalyst particles also there will be pores. Let me just blow this up and show you. Okay, so there are pores inside each catalyst particle, and between one particle and the second particle there will also be pores which are there. And when you put each of these pellets inside the reactor, there will be spaces between these pellets. That will be another porosity which we call the bed porosity. Just think about the bed porosity that you learned in your mass transfer classes, the same thing. So there are three kinds of pores that we have, porosity that we are talking about. But the names of micropores, mesopores, and macropores are essentially dependent on the sizes of these pores which are there. And inside the pores, if I blow up each one such site out here, this is what I get, where the actual reaction A going to getting attached to the active site by adsorption, reaction happening, and then B getting dissolved from that is happening. Catalyst preparation. Then comes the bulk or unsupported catalysts. How do we prepare these catalysts? Now, if you remember when I taught you about the different types of catalysts, I told you there are two primary types. One is called the supported catalyst and one is called the unsupported catalysts. And now let us see how do we prepare these. Now, the first one we are talking about is the bulk or the unsupported catalyst. If you do not remember, let me just remind you what they are. This is something where the whole catalyst is actually catalytically active. The whole catalyst is catalytically active, and that is why they're called bulk. So, for example, if I use alumina is Al2O3, aluminum oxide, it is an acidic catalyst. If I use aluminum oxide powder, then this will be called a bulk catalyst. Or if I use a whole zeolite, which is essentially silicon oxide and aluminum oxide together, then that is known as a bulk catalyst, where we are not putting anything on top, nothing is supported, etc. So the term that is important out here is the term that it is called a bulk catalyst, or you can also call it an unsupported catalyst, where the entire catalyst consists of the catalytically active substance. And how do we prepare such a catalyst? Here we will do a little bit of things like you did in your chemistry labs, but I will do it in terms of a flow chart, etc. So it is not like you learn up too much by heart. So the main preparation methods are either you use precipitation or you use gel formation. So the first thing that we talk about, the first method that we will discuss is the precipitation method. So this is the method of obtaining solid material in a porous form, and it involves, now let us look at the steps which are involved. The first step is adding a precipitating agent to solutions of a desired component. So we have a solution of the material that you want deposited, you add a precipitating agent to it, and then the precipitate forms. After the precipitate is formed, the precipitate is washed, then it is dried, calcined, and finally activated. Magnesium oxide catalyst is prepared by precipitating magnesium salt from a nitrate solution by adding sodium carbonate. So here we have, now what we are trying to form, which bulk catalyst are we trying to make? The bulk catalyst we are trying to make is magnesium oxide. And how do we make that? So we start off with a magnesium salt, which is essentially magnesium nitrate. This is a soluble salt, so it will be in solution. And so this is my first step. This is the solution of the desired component is magnesium nitrate, and to which I add a precipitating agent. So here my precipitating agent is sodium carbonate. So we are adding sodium carbonate to it. Immediately there's a reaction and magnesium gets attached to the carbonate to form magnesium carbonate and the sodium nitrate. Sodium nitrate will again go into solution. You know, all sodium salts are soluble in water, and magnesium carbonate essentially gets precipitated. This is my precipitate. Then you separate out, filter it out. You take this magnesium carbonate and you wash it with water to remove all traces of sodium. Sodium might actually act as a poison. So we have to keep on washing it with water, and so that we have only pure magnesium carbonate left, and all my sodium, any traces of sodium which are there are removed. Then you filter it, that means remove all the solution from it, keep on washing it with water, so there is only pure magnesium carbonate which is left. Then the wet paste is dried at room temperature. Then you keep this filtrate that you get, and you keep it and have it. The solid that you get, which is dried at room temperature. Room temperature means 30-40 degrees centigrade, whatever our room temperature is. And then we carry out another process which is known as calcination. Or we say that the solid is calcined. The calcine means that a solid is treated at high temperatures in an oven. you treat it at very high temperatures. Usually what happens is that you, suppose the bulk catalyst that you have formed, the dried solid, is at room temperature. Then from room temperature to this high temperature of 500, 600 degree centigrade, you slowly increase the temperature. Once you slowly increase the temperature, that process is known as calcination. And during this process, your magnesium carbonate decomposes to form magnesium oxide and carbon dioxide. So this is the process by which we form the bulk magnesium oxide, which can be then used as a catalyst. Here, before going into the next preparation methods or method of sol gel formation, I just wanted to stress a little bit on this calcination step. The last step that we talked about, that taking it up to high temperatures, this step is known as calcination. Calcination is often the last step in the catalyst preparation and is the heating of solids to a very high temperature after the drying process. The process of calcination is carried out to decompose the precursor and remove volatile materials. Now, let me just teach each one of precursor is like the starting material that you're making the final product from. So magnesium carbonate is the precursor, and you are heating it to very high temperature to decompose it or break it up to form magnesium oxide and carbon dioxide. So this is for the first. Why do you, supposedly someone wants to know that why is calcination actually carried out as a last step of my catalyst preparation? The reason we do that is the first thing is to decompose my precursor and remove all the volatile materials. So magnesium carbonate is broken up to form magnesium oxide, and the volatile material, the gaseous material of carbon dioxide, is released or removed. This leads to the formation of a well-determined pore structure. Now, as the gases pass through these solids, the porous structure is formed. The hydroxide form is converted to the oxide form. Chemically bound water is removed at high temperature. So all of these things happen during the calcination step. The second reason why you carry out calcination is to attain thermal stability. Now let's explain what this is. When we are talking about thermal stability, we can start off by saying that the catalyst sample is subjected to severe high treatment, to a more severe high heating treatment than that is likely to encounter in a reactor, to ensure the stability of its textural and structural properties during the reaction. So what does this mean? Suppose your this time that is carried out, that means the catalyst is exposed to a temperature of 600 degree during the reaction. That means your reaction is happening at a temperature of 600 degree. And if you dry the catalyst, etc., at 400 degrees centigrade, and you say my catalyst is prepared, then when you take this catalyst and put it in an atmosphere of 600 degrees centigrade, sometimes there's a decrease in the surface area of the catalyst. And that means my catalyst is still not thermally stable. Textural and structural means, say for example, the surface area gets reduced. This happens, we often see this, that when you heat the catalyst to very high temperatures, there's a collapse of the surface area. That means there's a decrease in the surface area. And so what we do, that suppose a catalyst will be used at a temperature of say 600 degrees centigrade, we actually treat the catalyst or calcine the catalyst at a higher temperature, say a temperature of 700 degrees centigrade. So it is exposed to a more severe condition than it will actually face in my industrial reactor. And because we are treating it to this high temperature, whatever decrease in surface area had to happen, that decrease was going to happen in the catalyst. So once it goes to a temperature which is say lower than this treated temperature, no more change in the surface area will happen. And the next thing is that means the surface area can decrease due to two reasons. That is, one is temperature and one is time. So this temperature is more or less due to a linear decrease in the surface area. And when we expose it to long times, also there's a decrease in the surface area. And the second thing is that what is called as structural properties. For example, certain materials, giving an example of say alumina, that means Al2O3, it can change from a cubic form. Here it is, the cubic form. When you heat it up, it can change to a monoclinic form and finally to a hexagonal form. So once you have done that if you heat treat it beforehand, so your catalyst, if it's not heated to high temperatures, might actually be in the cubic form. But once you're putting it in the reaction atmosphere of 600 degrees centigrade, it changes itself into an hexagonal form, and the behavior will be of a hexagonal alumina. So that it cannot be allowed. It should be treated to a condition where it already forms an hexagonal structure, and then you introduce it into the catalyst bed. So these are the reasons why we carry out calcination. Number one being to decompose the precursor, then to release all the volatile materials which are there, break up any water molecules which are there, then to attain thermal stability so that the final catalyst is stable in terms of its textural, here we have to use two terms, textural as well as structural properties of the catalyst has now become stable. So once you use it in an industrial reactor, there will not be any other changes which are going to happen in the catalyst itself when you have this reaction. So today I'm going to stop out here since you have a class after this, and on Monday we will take it up from here in the class.